Welcome to This Explainer. Today, we're diving into a massive philosophical shift in how we handle the messy, totally unglamorous backbone of machine learning. Yep, I'm talking about tabular data. For over a decade, data scientists have been reaching for the exact same familiar tools, building these incredibly complex pipelines just to force their data to fit the algorithm. But today, we're unpacking a framework that does the exact opposite. We're looking at a system built from the ground up, from first principles, to handle the wild, heterogeneous data we actually see in production. So let's uncover the hidden gem of tabular AI together. Okay, to kick things off, there's this machine learning proverb that I absolutely love. It goes, "In the forest of algorithms, the one that sees both numbers and names will find the straightest path." And honestly, this hits the nail on the head. It captures the real challenge we face every single day in applied machine learning. It's not just about crunching pure, continuous numbers, right? It's about natively understanding this complex, hybrid mix of numerical data and those tricky categorical names or labels. Because the algorithms that can truly see both, those are the ones that are going to perform at their absolute peak. Now, when traditional decision tree algorithms try to map out real-world information, they basically build out a literal forest of decisions. But look at how chaotic this gets. These trees can easily grow into highly complex, totally irregular structures. And sure, they're incredibly flexible, which is great, but that exact same flexibility means they can easily become super noisy, especially when you get into those small data-sparse branches where the algorithm just starts memorizing random noise instead of learning actual useful patterns. And honestly, that brings us to the data itself. We've all been there, right? Real-world tabular data is incredibly messy. It's almost never as clean as those polished data sets you see in textbooks or beginner tutorials. Out in the wild, it's this living, breathing patchwork of transaction histories, random product codes, timestamps, medical records, and just endless categorical columns. And usually, we're forced to build these tedious, super fragile pre-processing pipelines just to force-feed all this messy data into models that, frankly, were never really designed to handle it gracefully in the first place. So before we can even talk about a better way to do this, we've got to call out the bad guys. I like to call them the hidden villains, holding back classical gradient-boosted decision trees, stuff like XGBoost and LightGBM. Look, despite their massive popularity, they inherit some pretty severe systemic limitations. Specifically, we're talking about prediction shift, categorical leakage, and leaf-wise growth bias. These three statistical flaws are basically the silent killers of your model's generalization capabilities, and they are exactly what we need to overcome. Let's start with the most insidious villain of the bunch, prediction shift. This is a super subtle, almost invisible form of target leakage. You see, in standard boosting, residuals are computed from models that were fitted on the exact same examples, whose gradients are then reused. So technically speaking, the algorithm is literally peeking at its own answers. This weird self-influence distorts the gradient estimates and creates this accumulating bias that seriously harms the model's ability to generalize, especially when you're working with smaller or really noisy datasets. Which leads us to a pretty fascinating question. What if we redesigned gradient boosting today, entirely from scratch? Like, if we could wipe the slate clean right now, knowing everything we know about these statistical flaws, the target leakage, and all those practical day-to-day pain points, what would we change? How would we engineer an algorithm specifically built to respect the messy, chaotic reality of data without constantly falling into these statistical traps? Well, enter CatBoost. Originally developed at Yandex to replace their older in-house algorithm, CatBoost is a total game changer. It isn't just some minor engineering optimization of the old GBT formula. We're not just talking about making trees grow slightly faster or just slapping on GPU support. No, it's a complete first principles redesign of how boosting should actually operate. It treats things like categorical features and prediction shift as fundamental first-order problems that have to be solved at the algorithmic level, not just brushed off as annoying pre-processing homework for you, the data scientist, to figure out. So what makes CatBoost structurally so different? Well, we are going to break down its three distinct algorithmic superweapons, one by one. We've got ordered boosting, ordered target statistics, and symmetric, also known as oblivious trees. And to be clear, these aren't just little feature tweaks. These are fundamental design changes baked right into the core engine, specifically created to neutralize the exact weaknesses we were just talking about. Let's kick things off with ordered boosting. This is basically the direct mathematical antidote to prediction shift. How exactly does it break that nasty feedback loop? By establishing a virtual timeline. The training data gets randomly permuted, and for every single example, CatBoost computes its gradient using a model trained only on examples that come before it in that specific timeline. It mathematically guarantees that a row's residual is calculated while explicitly excluding its own target. And just like that, it completely removes that self-influence bias. And it does it without sacrificing the quality of the fit. Next up, CatBoost totally reimagines how we handle those endless categorical variables we all dread dealing with. Instead of the painful, signal-destroying process of manual one-hot encoding, CatBoost treats categories as absolute first-class citizens, using something called ordered target statistics. And just like with ordered boosting, it relies on that virtual timeline. When it encodes a category for a specific row, it only uses target statistics from rows earlier in that random permutation. What you get is highly powerful, self-leakage-aware encodings entirely under the hood, which means zero dimensionality blowup and absolutely zero direct target leakage. It's a total lifesaver. Now, beyond just how it handles data, there's a huge difference in how these frameworks actually grow their trees. Powerful tools like LightGBM use this greedy, asymmetric leafwise growth. And sure, that's fast, but it can easily overfit noise and tiny branches unless you do some meticulous hyperparameter tuning. CatBoost takes a completely different path. It uses perfectly balanced symmetric trees, or oblivious trees. This means it applies the exact same split at every single node of a given depth, completely across the entire tree. You might be wondering, okay, so why does a symmetric structure actually matter? Well, think of it like a perfectly balanced tournament bracket. At every single round, every match follows the exact same rule. This uniform structure acts as this incredible natural regularizer, inherently stopping the model from creating overly specific, noisy little branches. Plus, and this is a massive bonus for production, this uniform architecture enables incredibly fast bitwise scoring. Because the tree is perfectly symmetrical, it allows for highly efficient CPU vectorization. The result? Lightning-fast inference times that are absolutely perfect for low-latency environments. Of course, we don't have to just take their word for it based on theoretical design. Let's look at the receipts, because the empirical evidence is striking. In massive, completely independent benchmark studies spanning hundreds of datasets, CatBoost really shows its teeth. In the big NeurIPS 2023 study covering over 170 datasets, CatBoost achieved the best mean rank among GPDs, straight up beating out XGBoost and LightGBM. And in Shmuel's 2024 comprehensive benchmark of 111 datasets, CatBoost led all tree-based models, taking home the most best score wins overall. When you put them on an even playing field with uniform hyperparameter branchets, CatBoost consistently outranks the heavily marketed giants. And honestly, the evidence just keeps compounding. Check out the brand new 2025 Tab Arena Living Benchmark. It ranked CatBoost #1 among GBT frameworks in conventional tuning regimes. But the real takeaway is where it dominates. We're talking high cardinality datasets packed with mixed type features, and environments dealing with moderate to high noise. This basically proves that when your margins are razor thin and your data is just packed with messy categorical variables, CatBoost remains the absolute top-tier default candidate. Which brings us to a final provocative question to wrap up our explainer today. Is the best machine learning algorithm really the one with the most hype, or is it the one inherently built from the ground up to respect the messy, heterogeneous reality of our data? So as you gear up for your next tabular project, ask yourself, do you really want to keep wrestling with fragile manual pre-processing pipelines? Or are you ready to finally try the algorithm purpose-built from first principles for the real world? Thanks so much for exploring CatBoost with me today. Now go out there and keep learning.